All right. Last week we started lesson 5 on the binary number system, and we learned that this binary is the backbone of information technology. It is the blood of information technology. It is the veins of information technology. It is everything to information technology. And if you want to understand computers, how computers work, how IT works, this is one of the first lessons you should take. We looked at what we call bit and byte, and we said a single binary digit is called a bit, and a byte is 8 binary digits put together, known as a byte. We went ahead and we learned how to convert from decimal into binary by using several methods. We use the division method. We also use the positions method. And we also learned how to write in binary by just learning how to add one bit to the next bit. If I have 0 and I need to add 1 bit, I know that when I add 1 bit, I'm going to get 1. I know that for sure. When I have 1 and I'm supposed to add another 1 bit to make it 2 bits, 2 will be like this, 1 0. From 1 in binary number system, you move to 1 0. If you are supposed to add 1 bit to 1 0, you have to know that this is what it's supposed to be, 1 1. From 1 1, you have to know that 1 0 0 is the next bit. By just studying this, you can learn to add 1 bit. And by learning how to add just 1 bit to the next or the previous bits will help you a lot to be able to not only read but be able to understand binary to a certain degree and be able to write in binary codes. If you are not here, you have to pay serious attention to be able to understand what we have to learn today, because last time we learned how to do the conversions. If you are not here last week, you have to pay serious attention to be able to understand what we are going to build on or add to what we studied last time. You can also watch the previous lessons on the channel. In a few days it will be up. Then you will understand how it works. If you are given 1 0 0 0 and you are supposed to add 1 bit, you have 1 0 0 0 and you are supposed to add 1 bit, what is it going to be? 1 0 0. Excellent. This is all you have to learn. Now if you have this and you are supposed to add 1 bit, you have to know how to go about it. To add 1 bit, who can tell me how it's going to be? It's going to be 1 0 1 0, and the next one is going to be excellent. Next one is going to be 1 1 0 0. Then 1 1 0 1. Then next one will be what? Yes, 1 1 1 0. Next one will be what? 1 1 1 1. Excellent. So just learning how to add 1 bit to the previous bits will help you a lot. All right. So we use the division method and we learned how to convert and how to write it after converting and how to finalize your answer in 8 bits. We talked about how to finalize your answer in 8 bits. If the bits you get is not up to 8, what do? You add zeros in front to make it 8 bits. We learned that to convert from binary to decimal, this is a table you have to use. This is a positions table. In binary, this is a positions table. And last week I demonstrated how to use the positions table. And so to use this positions table, if you are given a number of codes to convert, all you have to do is to make sure your code is in 8 bits and you write your code inside this table. Once your code is inside this table, all you have to do is to pick the number where the ones are and add them. So here, when I see a code like this, for me as a person or as an expert, when I see a code like this, 0, 1, when I see this, I know this is 65. I know it. When I see this code, I can interpret it myself as 65. And I also know that this is the code for letter A. When it comes to text, this is a code for letter A. Now, how do you know it's 65? From experience, you will know. But when you load your code into this table, you will see that under 64 we have 1, and under 1 we have 1. You have to ignore the ones with the zeros and just add the ones with the ones. So 64 plus 1 will be what? 65. Who can tell me what this will give us? This will give us 25. Why? 16 plus 8 plus 1. Excellent. 25. Now, today we'll be learning how to convert from binary to text. From binary to text.
Hi, my name is Lamore Freed, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros. Or you may have seen scary-looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only 2 options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8th position, and so on. For example, the number 9 in binary is 1, 0, 0, 1. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only 1s and 0s, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page or your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, now we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
Without a lesson like binary, you can never understand computers. Maybe you can do some word processing or watch your movies or use a computer for certain things. But if you want to understand computers, without what we are talking about, it's not possible to understand computers. Because everything in a computer, even the electrical signals, are in binary. The data is in binary. Even sound we hear is binary. Images we see, binary. Videos you watch, it is incredible. You think you are watching videos. Meanwhile, it is just binary codes that is flashing on your eyes, but you can't see. In binary, you are seeing videos. Now let's see what happens when we see text on our screen and how the computer understands it in binary. So converting from binary to text. In order to convert from binary to text, the 8-bit binary code needs to be converted first into decimal and then translated into text using the Ascii encoding system. Please, are you here? To convert binary to text, it goes through 2 stages. Every binary code must jump into a decimal state first, then it will jump into an Ascii state. Ascii is an encoding system. Hello. Ascii is what? It stands for American Standard Code for Information Interchange. It is an encoding system. And this encoding system is one of the first encoding systems created to help translate characters or symbols into numbers and from numbers into symbols. You have to understand that we have some tables of representations, and these tables tell us the meaning of certain numbers in different forms. For example, every symbol has a number associated with it. Every symbol has a number. Hello. I said every symbol has what? Let me use this keyboard to explain something to you. I want to tell you that when you are using the numeric keypad, you can enter the number code for any symbol that exists in the world of IT. Whether you are using the Ascii encoding system or the Unicode encoding system. Watch this. When I hold the Alt key and I press 155 and I release everything, what do you see? What is on the screen? What is on the screen? Which symbol is that? Ghana city. I didn't. Do you see Ghana city on the keyboard? But if you want Ghana city, you have to know the ASCII code for Ghana city. And the ASCII code for Ghana city is 155. You need to use Alt to get it. So you hold Alt and you press 155. When you release, you get it. What I'm trying to tell you is that every symbol that exists has a code. And this code is found in a big table that was standardized or agreed upon. That this is a table we are creating for information technology. And so, according to this table, 155 means Ghana city symbol. According to this table, watch this. Alt 97 means what? A. 97 in the ASCII encoding system represents A. If you have your keyboard, press Alt 98. What will you get? I'm not pressing B that you see here. I'm using numbers. Alt 99. What do you see? Small c. Small c. If I want small d, Alt 100. Is that what you see? Now watch this. Please, are you here? So Alt 65. What did they give me? Capital A. What's this? So Alt 97. What did they give me? Computers do not know that big A and small a means the same thing to human beings. They don't know. There are different symbols to the computer. And so we have different codes for each one of them. If I want capital B, Alt 66. Small b is Alt 98. Let me tell you, capital A begins at Alt 65. If you want capital B, is Alt 66. Capital C, Alt 67. Capital D, Alt 68. Are you following? 69 will give us what? E. Now watch this. Small a begins at Alt 97. Now I said capital A starts from when? It's what? 65, right? And small a is what? 97. All I need to remember is 97 and 65, because if I want to get C, I don't even have to remember C, I just have to remember A. Then I just add. So if you know that capital A is 65, so what will be capital C? Or 67. Okay. Are you with me? If you are supposed to spell your name with your computer keyboard, let's say your name is Amma, we'll start with capital A. So we need to get Alt 65 for the capital A. I want you to find the code for small m, not capital M. Find the code for small m for me now. Who has gotten it? Now listen, if you want to get the code like this, or you want to get symbols or text from the code, this is the only part you can use. You can't use numbers from here. So the reason why I came for this keyboard is because my notebook is not having the numeric keypad. If you have a laptop that has a numeric keypad, then you can use it. If not, you need to get a desktop keyboard with a numeric keypad. Let's say your computer keyboard has a problem, or let's say you have a laptop and some keys are not working. After learning the Ascii encoding system, you can use the numbers to get those letters. For example, someone's laptop, the T on the laptop keyboard, the T has removed. The key is not there, so he's not able to get T. One way is to use the Ascii encoding system to press Alt and the number for T. You have to learn it. What's the number for T? You learn it and then you enter it, and it will show. Anytime you want T, it will show, or any letter at all, or any symbol at all. Now you have to understand that Ascii, one of the first encoding systems created for computers, and so it doesn't cover every symbol in the world. And so we will look at the Ascii table and you see how it is. But we have other encoding systems like the Unicode that covers every known symbol in any language, in any culture, in any part of the world. All right, so what is small m? 109. So that is it. And small a is what? I already taught you. Not 65. 65 is capital A. 97. So I hold Alt and 97. Remember, you need to hold your Alt before you press it. Now, what I'm demonstrating to you is what we call the Ascii encoding system. All I'm telling you is that these things, the computer sees them as symbols. You understand them as English letters, right? The computer doesn't know that. It knows these things as symbols. And each symbol, there is a number assigned to each symbol that exists. Any symbol you want, you just have to go and find a number for it. Any symbol at all, you just have to go and learn the number for it. If I type out 1 2 4 5 and I release, you see that something has appeared. Out 8 5 4 and I release. Out, this is a symbol has appeared. So I just entered 2 3 5. Let me try it. Out 2 3 5. Out 2 3 6. You see, this is infinity symbol. Out 2 3 6. So there's a code for every symbol that exists under the sun, so that computers can communicate in other languages and any language. All right. So when you are asked to convert from binary to text, you have to understand that you have to convert first of all from binary to decimal. Once you get the decimal number, that decimal number represents the ASCII code for the letter you are looking for. So let's convert this code into text. 01000001. How can we convert this into text? Pardon? We have to, let me bring our conversion table, the table. All right. Now, with the table, you have to know that there are 8 columns because of 8 bits, and the positions start from here. We have the ones positions, we have the what, twos positions, then what, 4. Okay, so you can just do it this way. So we have 1. When you add 1 to 1, what do you get? 2 plus 2 is what? 4 plus 4 is what? 8 plus 8 is what? 16 plus 16 is what? 32 plus 32 is what? 64 plus 64 is what? 120. So this is how to get the table. So you do it that way till you get to the 8th position because of 8 bits. You know that 8 bits is a standard. So you get here. Now once you have this table, any number they give you, let me give you any code and you should be able to tell me what that code is. What is this? 5. Excellent. You can just add this and that to get 5. What number is this? 14. So when you are asked to write 14 in binary, it's 1110. Because we have the 8th position, 4th position, 2's position, and 1's position. I explained this the first time. So to understand binary code in terms of in decimal, you can use positions to tell. Once you understand the positions table, you can use the position to tell. Okay, now we were given a certain code to convert into binary. So we have 01000001. From this positions table, when I load the code here, that's it. It's what? 65. So you can see how easy it is to convert from binary to text. If I'm given this binary and I'm asked to convert it into text, first of all, I'll convert it into decimal and I know it is what? 65. Now I need to convert 65 to text using ASCII encoding system. I'll just have to hold Alt and press 65, and what will I get? A. So this is the code for A in binary. Are you with me? We are converting from binary to text. Let me give you another binary code. Okay, This is my binary code. You are supposed to convert this to text. Please, have you seen this? Good. What will you do? How can you convert this binary code to text? How can you do it? Yes, who can tell me? Excellent. So first convert this to decimal and then convert to text. So 0 1 0 1 1 0 1 0. I'll come and feed it here. 0 1 0 1 1 0 1 0. Is that not the code? What is the number? What is the decimal number we get? Okay, we get 64 plus what? 16 plus what? Plus what? 8 plus what? Plus 2. What do we get? What do we get? 90, right? 90. So after converting this to decimal, I know I have 90. How to convert 90 to text? I don't have to worry. I just go to the Ascii table and find what 90 stands for. I can use my keyboard Alt 90 and I'll get what? Capital Z. This is the code for Z in binary. When you press Z on your keyboard, this is what is stored in the computer. Are you with me? Please, are you sure? You are very sure. Okay, I'm going to give you a simple exercise. All right, so how do we convert a code like this? If you are given a code like this, how do we convert it into text? First of all, we'll break it into 8 bits. This is the first 8. 1 2 3 4 5 6 7 8. This is the next 8. 1 2 3 4 5 6 7 8. This is the next 8. Let me see all that I was writing here. Were they even up to 8? Oh no, I made a terrible mistake. So they are supposed to be in 8 bits. It's always 8 bits, right? Good. So first of all, I will feed this code into my table, and when I feed the code into my table, you know what I will get, right? So when I feed it into my table like this, it's going to give me this, and this I know it is 64 plus what? 1, which is equal to what? 65. So over here, I know that the first part here is 65. How do I convert 65 to text? I need to check from the Ascii table. If I have a keyboard, I'll just use my keyboard. Alt 65. You see, I got 65. I'll type Alt 65 and I'll see the letter. Okay, now I'll move to the next 8 bits. Okay, I'll feed this code into my positions table. This is what I'll get. It is 64 plus 2, 66. 66. What is 66 in binary? Sorry, in text. What is 66 in text? So this is 66. This is 66, and 66 stands for Alt 66. Let me type Alt 66. Then I'll reveal it. I will not type what I think it is. I will use Alt to input it, and whatever appears, I will know that it's correct. Or I'll use the Ascii table. Let's finish this. This is a simple one, so let's just finish this. This one, if you feed it into it, what will you get? 65, and it will be what? Capital A. So we know that the message is what? ABBA. Okay, someone may be called ABBA, or ABBA may be acronym for something. All right. Now, I'm sure when I give you any binary code, you can give it to me in text. Very soon, I'll give you text and I'll tell you to reveal it in binary for me, and I know it's going to be simple for you. When I give you text and I say, tell me the text in binary, I know it's going to be easy for you to do. Because when you finish doing all these things, you are going to write your name in binary. And your telephone number. Next time when someone asks you for your telephone number, you give it to them in binary. All right, let's read what we have here. The Ascii encoding system. So now you are getting an idea of what the Ascii encoding system is. It is, let's read what it is. Ascii is an encoding system known as an abbreviation for the American Standard Code for Information Interchange. Well, let me rephrase it. ASCII stands for American Standard Code for Information Interchange. That is ASCII. As you advance in IT, and if you want to be a computer science student, you'll be learning about different encoding systems. But as for ASCII, is the most basic one that every beginner learns. ASCII. Now, ASCII is a simple encoding system. It is made up of code numbers for 128 characters. So when it comes to ASCII, we have 128 characters, which includes 10 numbers. It even has numbers. So we have number code for numbers, plus the 26 English alphabets, punctuation marks, and various symbols. So in ASCII, if you want to be more technical, ASCII has 128 characters. Every text character has an associated ASCII code in decimal value. Therefore, whenever binary needs to be converted into text, all that needs to be done is to find out the decimal value of the binary code. And that value will then be represented, or will then represent the ASCII code for the associated character. So for example, when binary code is given to you, like 01000001, all you have to do is to convert it into decimal. Once it's in decimal, you just bring the decimal into the ASCII table and find out which symbol it represents. ASCII is all about symbol representations with numbers, with decimal numbers. Okay, so that's it. So for example, the decimal value of the binary code is 65. This decimal number is the ASCII text character for the English alphabet A. Please, you already understand it, what I'm reading. So we have what we call the ASCII table. Have you seen the ASCII table? This ASCII table tells you the ASCII codes for various symbols. Okay, now what do you see here? Dollar, right? And what do you see in deck? 636. Okay, type Alt 36 on your keyboard and see what you get. Alt 36 if you have a keyboard. If you have, what did you get? So if you are supposed to produce a dollar symbol and you don't have it on your keyboard, if you know ASCII, you know that it's 36. So Alt 36 will give you dollar. The idea is that all the symbols here, they have an associated decimal value or number. If you check here, 65 is what? Is it capital A? If I want G is what? Capital G is what? 71. Now, when you are given, let's say, a text like M, and they say find small letter m, find the decimal number for small letter m, all you have to do is to come to the ASCII table and locate small letter m, and you see the decimal number is what? 109. Do you remember I asked this question and the person said 11 something? Okay, so it's supposed to be 109. With the ASCII table, you can produce any symbol. Look at the @ symbol. The @ symbol is what? Number what? 64. So if you want @, let's say you are supposed to type @, you are sending an email You can't find art on the keyboard, and even the key that is supposed to bring art is not even working. You can hold your Alt key and type what? It is the same thing. So with numbers, we can get all symbols and characters and texts. All the text we want, we can get them from numbers. Isn't that a little incredible? All right. So now, if let's say your name is Rena, and you are asked to write your name in binary, what will you do? Who can tell me? How can we go about this? You are supposed to convert this name into binary code. How will you do it? You go to Ascii table and do what? Decimal value of what? Of Rena? Of Rena. Do you have Rena in the Ascii code? Ascii table? Okay. So you find the decimal value of each letter. Remember, R here is capital R, not small r. Small r has a different value. What is the decimal value of capital R? Let's check from the Ascii table. R is what? 82. So I will come here and type 82 space. Small e is what? Small e. 101, right? Small I is what? 105. Let me confirm. She said 105, eh? 105 is small I. Excellent. You are right. Okay, small n. Small n is what? 110. And small a, you know, don't look into the book. 97. So if I'm asked to convert text into binary code, this is the first step. I'll convert the text into decimal. How can I convert text into decimal? How can I do that? I said to convert from the text into binary, I'll convert from text to decimal. How in the world can you convert from text to decimal? How in the world can you convert from text into decimal? You can do that by using the Ascii encoding system or the Ascii table. Does that make sense to you? Good. So now that you have the decimal, you can easily convert your decimal into binary. So when you are given 82 to convert to binary, how will you go about it? The last time we met, we learned how to convert from decimal to binary. Okay, you can either use the division method or the positions method. So let me use this positions method and see what we will get. For division method, you remember the division, right? Okay, so the number is what? 80 what? 82. So first of all, come up here and find the next number lesser than 82. So we will know that 64 must come in, right? So we'll put 1 here. Okay, so what can we add to 64 to get 82? 64. When we add 16 to 64, what are we going to get? When we add 16 to 64, what are we going to get? We are going to get 80. So this one can also be part, right? And which one can be part? 2 can be part. So the code is going to be 01010010. That's the code. So this is using the positions method. To use the division method, let's see if we'll get the same code. Let me come here and we'll use the division method. With the division method, we said you enter your number is 80 what? 80 what? 82, and then you type remainder. Now, how many times will 2 go into 82? Pardon? 41. 41. Remainder what? Remainder 0. How many times will 2 go into 41? 20. Remainder what? How many times will 2 go into 20? 10. Remainder. How many times will 2 go into 10? Remainder. How many times will 2 go into 5? Remainder. How many times will 2 go into 2? Remainder. How many times will 2 go into 1? Remainder. Now, to read the code, you read it from the bottom, right? So we are going to get 10 100 10, right? Good. Now let's leave our answer in 8 bits. How many bits do we have? How many bits do we have? There are 7 bits. So to leave our answer in 8 bits, what are we going to do? Add 0 to the beginning. So 0 1 0 1 0 0 1 0. Are we seeing it? Let's go and check with the positions method and see if it's the same. Is it the same? It's the same. So which is easier, the divisions method or the position method? They are all easy. Any number you are given, you can convert. So now I've converted the first, and you have to remember to leave your answer in 8 bits. So I've converted the first letter into binary. That is it. So I'm done with the first one. Next, we'll go and pick the next number and you convert that as well. Let's use the positions method to convert 101. 101 using the positions method. First of all, let me change all these to zeros first, and we start. 101. First of all, you pick the number lesser than 101 from the top here. So what are we going to get? 64 will be part, right? Okay, 64 will be part. 32 2 has to be parts. So 64 plus 32 is what? 96. Okay, 96. What can we add to get 101? 96. What do we have to add? We have to add 5, right? We have to add 5. Or 96 plus 5. Okay, we don't have 5 here, so we'll pick 4 and we'll pick what? 1. So this is a code. It's going to be 0 1 1 0 0 1 0 1. Let's try it with the division method and see if we'll get the same. So we have 101 remainder. How many times will 2 go into 101? 50. Remainder what? How many times will 2 go into 50? 25. Remainder. How many times will 2 go into 25? 12. Remainder. How many times will 2 go into 12? 6. Remainder. How many times will 2 go into 6? Remainder. How many times will 2 go into 3? Remainder. How many times will 2 go into 1? Remainder. Okay, now we read it from the bottom. So we have 1 1 0 0 1 0 1. How many bits is it in? 7. So we need to leave it in 8 bits. So we'll bring 0 to the beginning. 0 1 1 0 0 1 0 1. Let's compare this to what we got here and we check if they are the same. Are they the same? Okay, so you can use the positions method or the division method. So now we know the code for the next letter. When you are asked to convert from binary to text, you have to convert them letter by letter. So this is what I have. This is for the first 2 letters. I can leave them this way or I can separate them in 8 bits. When I finish and I join them, or if I'm asked to leave them like this too, I can do that. Now, the next three I want you to convert for me. 105, 110, and 97. Do that for me. Okay, fine. So 105, let's convert 105 into binary. Let me use this method. 105. Okay, so 105, I know it's not up to 128, so I'll pick 64. I can also pick 32. Then 32 plus 64 is going to be what? 96. So I need 105. What will I add to 96 to get 105? 8 and 1. So that's 9, right? So 8 and 1. So the code is 011010001. Is that what you got?
Yes.
Excellent. All right. Now 110. Let me convert 110. To convert 110. I'll pick 64. I'll pick 32. That'll be 96. What will I add to 96 to get 110? 8, 4, and 2. Okay, so 8, 4, 2 will be 14. 14 plus 96, 110. Excellent. So the code is 011011110. Is that what you got? Beautiful. Did you use a division method or you use this method? Okay. So the last one is 97. We'll see how we convert 97. Okay, 97. We will need 64. 90, 32. That will be 90 what? 6 already. So we just add 1 from here. So this is very simple. 011000001. Is that what you got?
Yes.
Excellent. So now we are done converting RENA into binary. If you are asked to separate your code in 8 bits, then you separate. If not, whenever you see this code on my screen anywhere, it is RENA. Look at it very well and say, oh, RENA. It's RENA. This is RENA. All right. So by using Ascii, we have been able to convert from binary to text, and we have also been able to convert from text to binary, and everything is fine. Now I'll just give you a simple assignment and we will end here. Next time we'll learn how to convert from images to binary, or how to represent images in binary. So when you come, we'll learn how images are converted into binary. Remember, whenever you see a picture on your screen, you are seeing a picture, but the computer is seeing code, binary. It is binary that is put together to form a picture. And when you are watching a video, it is binary put together to form a video. So it is billions of binary codes that you see when you are watching videos. You see people, but everything is code, binary in the system. So I'll give you a simple assignment and we'll end today's lesson here. Next time we'll get into images, and after images we'll learn how to convert sound into binary. How do we convert sound into binary, or how does a computer convert sound into binary? Okay, at least even if you are not converting, you need to understand how it works. This is computer science. This is what you have to know. All right, so I want to thank you for joining us in this class. Next time we'll continue and we'll learn more.